Welcome back to Ace the Exams. I am your strategist, and today we are tackling one of the most notoriously tricky areas of the Cambridge 0625 physics syllabus, the thermal properties of matter. We're transforming the textbook science of thermal physics into a masterclass on exam strategy. Today, we're not just going to passively memorize formulas. No, we are going to look at formation, tactics, and execution so you can outplay the defense of those tough Cambridge exam questions. It's about bridging the gap between the macroscopic objects you can see and the invisible microscopic kinetic energy driving their behavior.
To kick off Act 1, the challenge, I want you to think about this actual real-world Cambridge past paper question. Explain why a solid steel train wheel needs to be heated before it's fitted onto a track axle. Now, let's look at two typical students taking this exam. We've got Alex. Alex overloads his answer with raw physics facts but provides absolutely no analysis. He just dumps everything he knows about heat onto the page. Then we have Sam. Sam rushes. Sam completely misses the command word requirements and just writes, "It gets bigger." Both of these answers are getting covered in red pen marks by the examiner. You cannot afford to lose easy marks like this. Keep this train wheel question in mind because we are going to build the exact strategy needed to score a perfect 100% on it.
Our game plan for today covers 4 key tactical zones. 1. Thermal expansion in action. 2. The specific heat capacity math. 3. Investigating changes of state. And 4. The physics of evaporation. Let's get right into it.
Okay, moving into Section 1, Thermal Expansion in Action. This is where we initiate Act 2, our strategy reveal, and start decoding those assessment objectives.
Now look at this classic classroom experiment. This brilliantly illustrates the concept of thermal expansion. On the cold side, the metal ball's diameter is just small enough to slip right through that brass ring. But after being strongly heated, it expands so much that it's literally physically trapped. It's not going anywhere until it cools down. Now, before we break down exactly how to structure your exam answer for this using our Peel framework, I need your attention for just a second. Before we continue, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to outsmarting the examiner.
So the crucial point here is understanding exactly how to define this for maximum marks. Thermal expansion is the increase in volume of a material when its temperature rises. This is where top students apply the Peel framework: point, evidence, explanation, link. Your point is that the volume increases. The explanation is the microscopic behavior. The atoms themselves aren't actually getting any bigger. Instead, as we add heat, those internal particles gain kinetic energy. They vibrate and move around much faster, and because of that chaotic energy, they physically push each other further apart. They literally demand more space to accommodate all that extra energetic movement. If Alex had just used the Peel framework to explain the kinetic energy instead of just writing "heat makes it huge," he would have nailed the question.
We actually harness this expansion in real-world engineering, and Cambridge loves testing you on applications. Notice this bimetallic strip. It's made of 2 entirely different metals bonded together: copper and an alloy called Invar. Different materials expanded completely different rates. Because copper expands significantly more than Invar when exposed to the exact same heat, the strip is forced to curve, with the copper stretching out on the outer, longer edge. This differential expansion makes for a highly reliable temperature-activated switch in fire alarms. So, if the command word is explain, your link in the Peel framework is connecting the unequal expansion directly back to the physical bending of the switch.
Now we are entering Act 3, the transformation. Let's transform those red pen marks into green check marks. When comparing states of matter, gases expand far more than liquids or solids for the exact same rise in temperature. Why is this? Because particles in a solid are locked into a tight structural grid. It is incredibly difficult to push their neighbors aside. But in a gas, those fast-moving particles are totally free to fly around, making it so much easier to violently push the walls of their container apart. So if you get a comparative question, structure your answer to explicitly contrast the tight bonds of solids with the free-moving kinetic nature of gases. That is your physics success blueprint in action. All right, moving on to Section 2, the specific heat capacity math. We know heat causes expansion, but how do we quantify the exact amount of thermal energy a system absorbs?
Specific heat capacity is an absolutely fundamental concept. When Cambridge asks you to define it, you must use precise terminology. It is the energy required per unit mass per unit temperature increase. Basically, it's the exact amount of energy needed to raise the temperature of 1 kilogram of a specific substance by exactly 1 degree Celsius.
It's essentially a measure of how stubborn a material is when you try to change its temperature. A high specific heat capacity means you have to pump in a massive amount of energy just to see that thermometer budge even slightly.
Look at these extracted values. They tell a fascinating story that examiners love to test. Water requires a massive 4,200 joules to heat up by just 1 degree. Meanwhile, gold only takes 300 joules. This perfectly explains why a metal pan on your stove gets burning hot in mere seconds, while the water inside it stubbornly takes minutes to actually boil. The metal has a very low specific heat capacity, meaning its temperature skyrockets with very little energy applied. Water, on the other hand, is a complete thermal giant by comparison.
When you get a 6-mark question asking you to describe an experiment to measure this, you need a rigid structure. You just need to logically follow these 4 steps. First, use a balance to measure the exact mass of your material. Second, accurately record the initial starting temperature. Third, heat the block and painstakingly record the exact joules of energy used on a joule meter. And fourth, wait for the thermal energy to fully distribute, record the highest peak temperature, and run your calculation. Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's transition into Section 3, investigating changes of state. We've mastered how energy usually changes an object's temperature, but what physically happens when matter transforms entirely from one state to another?
Welcome to Act 4, our interactive workshop. I am putting 60 seconds on our imaginary visual timer for Challenge 1, the data scan. Look at this complex heating curve of ice turning to steam. I want you to extract the core trend. What is the most important feature here? Time's up. If you notice the completely flat horizontal lines, you are thinking like an examiner. Notice how when the ice is melting and the water is boiling, the temperature line stays absolutely, perfectly flat even though we are constantly supplying heat. It holds exactly at 0 degrees and 100 degrees.
Now for Challenge 2, find the flaw. Imagine Sam writes, "The temperature stays flat because the heat stops working." That's a massive flaw and scores 0. Here is the examiner commentary on why. During a state change, that thermal energy doesn't just vanish. It is actively being used to physically break the chemical potential energy bonds holding the molecules together rather than making the particles move faster. Since temperature is literally just a measure of average kinetic speed, the temperature temporarily stops rising until the entire state change is entirely complete. Energy is breaking bonds, not increasing speed. Write that down.
Let's bring it home with Section 4, the physics of evaporation. This is a phenomenon that happens around us every single day, well below the boiling point, and is highly testable.
Get ready for Challenge 3, speed writing. You have 30 seconds to write one perfect Peel paragraph explaining this image. Go. Evaporation is basically a microscopic escape room. In a liquid, particles don't all move at the same speed. The ones that are randomly moving the absolute fastest, possessing the highest kinetic energy, are the only ones capable of breaking free from the attractive forces at the surface of the liquid. They launch themselves into the air. If you applied the Peel framework, your explanation focused on the high-energy particles, and your link connected it to escaping the surface. Brilliant.
Entering Act 5, the final system. Look at this stark contrast. Because Cambridge loves compare and contrast command words, boiling is a violent reaction happening throughout the entire liquid, but strictly at a specific temperature. That's why you see bubbles forming at the bottom. Evaporation, however, quietly happens exclusively at the surface with absolutely no bubbles and can occur at practically any temperature. Puddles dry up on a chilly day, right? Knowing the tactical difference between these two definitions guarantees you marks when they try to trick you. Here is our complete physics answering system. 3 rules guaranteed top marks when asked how to increase evaporation. 1. Command word decoding. If they say state, just list these. If they say explain, use Rule 2, Peel. Higher temperatures give more particles the energy to escape. Larger surface area gives more particles a clear exit path. Blowing a draft across the surface sweeps the escaped gas particles away so they can't fall back in. And Rule 3 is the time management matrix. Don't spend 10 minutes on a 3-mark question. Hit your 3 Peel points and move on.
Because the highest energy particles are constantly leaving the liquid, the average energy of the liquid left behind naturally drops, cooling it down.
This is the exact biological physics behind why we humans sweat to regulate our body temperature and essentially stay alive. Now listen closely. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
We've covered everything from the macroscopic expansion of train wheels to the microscopic escape of sweating water molecules. So I will leave you with this final, provocative thought to ponder. If evaporation naturally acts as a microscopic refrigerator, constantly drawing thermal energy away, how could we strategically engineer this ancient physics principle to cool our modern buildings and cities without using a single watt of electricity? The physics you just learned could literally save the world. Keep questioning, keep strategizing, and I'll see you in the next session.